All right, guys, we're going to do a few more problems together today on choosing a good U, and then what I call sometimes kind of funky U substitution problems. This won't be as long as what you did on Friday, but I feel like you probably need a little more clarification. Practice is your best asset with these. At first, choosing U and executing the problem can seem real unusual, but the more you practice, you're just going to get more of a rhythm for how these work. Now, since I'm asking you for average value, I want to remind you that the average value formula or memory trick I use is integral over interval. And our integral would be the integral of f of x, so ln of x over x dx, from 1 to e to the 4th over the interval, which is e to the 4th minus 1, which is always your upper minus your lower bound, or your right hand minus your left hand boundary. Okay, so I need to pick a u. You never let u just equal x, because if you did, you would wind up rewriting the problem as ln u over u du over e to the 4th minus 1, which doesn't help you at all. So u is never just x. Keep that in mind. Well, on this one, you may be thinking, well, it's not obvious that I have a composite function here. So sometimes what you need to think about is, I'm kind of looking at this and thinking I've got 1 over x and ln x in my integrand. Well, which one is the derivative of the other? So if you're saying, yes, if you take the derivative of ln x, you get 1 over x, that's giving you a hint to let u be ln x. And you saw one like this the other day with sine and cosine, which we made it a u substitution 2 in a row, and then the next time I showed you, I picked u more wisely. So a lot of times a good rule of thumb is that you want u to be as much as possible. You can make it small, but sometimes the bigger you make it, the easier it is. Now, I'm going to say that du dx, so the derivative of u with respect to x is 1 over x. And then I say du is 1 over x dx. Guys, what you're going to see me do is begin to chop this step out and just go straight to du, take the derivative and stick the dx on the end, and that'll burn a step. You don't have to do that, but you may. So now I'm going to say 1 over e to the 4th minus 1. I'm going to pull that separate. And then I'm going to say that the ln of x part on top is my u. And then where I would have 1 over x dx, I'm going to say, nope, that's my du. So really, I've only got one more thing to do, and that's to deal with limits. So remember, e to the 4th is my high x. So I need to find a high u. So my high u would be ln of e to the 4th, which is 4. So I'm going to put that here. 1 is my low x. So now I need to find a low u. So I'm going to say ln of 1 is just 0. So my low u is just 1. Okay, now this is not going to be a difficult problem, because I'm going to say, well, the antiderivative of u is 1/2 u squared, and I'm going to go 4/0 there. So I've got my first fraction, 1 over e to the 4th minus 1, times, when I plug in 4 squared is 16, half of 16 is 8. And when I plug in 0, half of 0 squared is just 0. So I'm going to wind up with 8 over e to the 4th minus 1. Okay? Sorry, you can hear my dog barking in the background. Now, on this problem, I want to find the antiderivative of tangent 3x secant squared 3x dx. Well, what I did the other day was said, let me let u be 3x, but then du would be the derivative of 3x, which is just 3 dx. The problem is, then I rewrite, and I've got tangent u secant squared u, And then dx still needs to be replaced, and I can see that dx would need to be 1/3 du. Well, I can certainly go again and do a second round of u-substitution, but that seems a bit more difficult. So let me choose my u a little more wisely. What if I let u be either the tangent of 3x or the secant of 3x? Now, technically, I could do it either way, and I'm going to show you both ways just so you can see how this plays out. But if u is tangent of 3x, then using the chain rule, the derivative of tangent is secant squared 3x times the derivative of 3x, which is 3, and then I'm going to tag the dx on the end. Sorry, my dog's barking. So, guys, in this case, the tangent of 3x here becomes your u. To replace secant squared 3x dx, I would need to divide the 3 over, so I would have 1/3 du. Now that's doable. That's an easier way to look at it. And then I know that's 1/3. The antiderivative of u is 1/2 u squared plus c. So it's 1/6. Replace your u. So u squared would be tangent of 3x squared, which is tan squared 3x plus c. Okay. So I could also go about this. I'm not going to do the whole problem, but I want to just show you. I could have said u is secant of 3x. Then du would have been secant 3x tangent 3x, and then times 3, the derivative of the 3, and then the derivative of 3x and then the dx. Well, if you write the original problem as tangent 3x, secant 3x, secant 3x, dx, then that means this part is becoming my u, and then all of this part with that tagged on becomes my du. So, well, it would wind up being 1/3 my du. So I would wind up in the exact same place. But for me, again, if I'm looking at which do I let u be, it occurs to me that the derivative of tangent is secant squared. So that's a u, and this becomes part of my du. I think it's a little easier. So one last problem. It's the same kind of thing. I'm just changing the types of questions I'll ask you. So on this one, I want to solve the differential equation generally. So that means I'll have a plus c in my answer. Remember, this is a differential equation because I'm giving you the equation for a derivative. So you are going to be done when you've got y equals the original equation before it's been differentiated. That's what the solution of a differential equation is. So remember, the first thing you have to do is separation of variables, which simply means get all of your x's on one side and your y's on the other. Then you take the antiderivative of both sides. Now remember, this is technically saying what's the antiderivative of 1 if you're integrating with respect to y. So that's just your y equals. So all the action really takes place on the other side. So now what I've got to do is figure out, well, do I want my u? And generally your u is not going to be sine squared or cosine cubed. It's going to be sine or cosine. Well, let me just say, let's go with sine x. And then I can show you how it plays out if you were to choose u equals cosine x as well. So the derivative of u is cosine x dx. Okay, so now I'm to the point where sine squared x becomes u squared. But this cosine cubed dx, I mean, that's going to give me cosine x dx times cosine squared x. And you might think, well, that's a weird way to write it, but this is my du. But I've still got this weird cosine squared in there. Okay, let me back up and show you something. All right, so I realize that I'm going to have sine squared x, and then I know down here I'm going to have cosine x dx, so that this is going to be u squared, and that's going to be du. But I've still got this cosine squared x hanging out there. All right, now you get creative with your use of Pythagorean identities. So you need cosine to an even power, because if it's cosine to the fourth, you could do this and then square the whole thing. Or if this was cosine to the sixth, you could do what I'm fixing to show you and cube the whole thing. But remember, the Pythagorean identity for cosine squared is 1 minus sine squared. And then I've got cosine x dx. Now let's replace, okay? So sine squared x is u squared. 1 minus sine squared is 1 minus u squared. Cosine x dx is du. Now, you never try to take the antiderivatives until you get it into antiderivative form. So that means you never have a product or a quotient. You go ahead and try to multiply or divide, separate and reduce is a lot of times what we do. So I have u squared minus u to the fourth du. Now I'm starting to see how it's going to work itself out. So I see 1/3 u cubed minus 1/5 u to the fifth plus c. So the only thing left to do now is to say u is sine x, so sine cubed x minus 1/5 sine to the fifth x plus c. And there you go. That's it for this video.